if you rewind the video, you'll realize that I had 2 red cards, and then I had 3 black, followed by 3 red, followed by 3 black, actually, followed by a red. Okay. Now, just in the speaking of those words, you may have noticed that I essentially said the same thing twice. Okay, there was a similarity to the sets of cards that we set out. Okay, and so what you'll notice here is we actually started with a 2-cycle structure. Now, a 2-cycle structure is where there is a repeating pattern. Okay, now we're only focused on colors, remember. So we have red, red, black, 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 red, and then we have red, red, black, black, red. This is cyclic. Okay, so this is a cyclic construction. Well, if it's cyclic, there's certain things you can do with that structure and not harm it, not change it from being what it is, namely a 2-cycle with cycle length 6. Well, one thing you can do is random cutting. You can cut anywhere. That won't hurt a cyclic packet. Something more powerful is the Charlier shuffle, which is used extensively on this channel. Okay, so this, all of the action here of the card movement of the cards here is equivalent to just cutting the cards at some location. Okay, so it's really just a card cut is all it is, so it doesn't hurt the intrinsic nature of this 2-cycle. From there, what I did was I did a Klondike shuffle. And if you remember, a Klondike shuffle, this is where you take the top and bottom cards off as 1 and then build a pile that way. It converts 2 cycles to mirrored structures. Now, once it's mirrored, we have a whole universe of mixing procedures that will not harm mirrored constructions. And that's primarily because of something called the stay stack principle. Okay, so with the stay stack principle, you can deal out into as many piles as you like this, as long as the number of piles is a divisor of the packet size. Well, 12 has several divisors. 2, 3, 4, and 6 divide evenly into 12. So we can deal out into 2, 3, 4, or 6 piles in the way that I've shown you here. With random stacking from left to right or right to left, we can even do what I've called a leapfrog stacking, which is something I actually used when I did the 1, 2, 3, 4, and so forth. And then I think you put the top piles on top of the bottom and so forth. None of those hurt the fact that it's mirrored at this stage. And then I Klondike the cards into just random pairs on the table. Well, they're not really random pairs, but I'm kind of scrambling the order of the pairs. And then I gave you the choice of building 2 piles of 6 cards each, one for you and one for me. Okay, and we did that by picking up any of the piles. So I picked up this pile last time as well, the one at the top. And then I gave you the choice. You could use as the bottom card of your pile either one of these. So maybe you want the top one as the beginning of your special pile, and then the other card will be the beginning of my special pile. Then maybe we'll choose this one. Which one would you like? That one there, this one here, and so forth. Now, the thing you have to realize is that because it was mirrored and I Klondike shuffled pairs to the table, this is called a DMP. What's a DMP? Well, in this specific case, it means that all of the pairs are already matched up in color. Okay, these are already, now these aren't anymore because we split them, but the key is each of these pairs consists of either 2 red or 2 black. Well, it's kind of a false choice here. If I say, which one do you want? It doesn't actually matter because they're both going to be the same color, so they're both black. And then the other black card goes here. Now, you wouldn't look at them, right? We just allowed them to choose. They maybe choose a black. That one there, it was black. The other one goes here, which is also black. Okay, here's a red. And then they'll choose either one of these or both red. But if you notice, at each level, as we're building these up, they're of the same color. Okay, that's essential. Okay, so now these are both black, so you'll choose just one of those black cards. The remaining black card goes on mine. Well, these are called coupled piles. Coupled piles because at each level of these piles, the cards are of the same color. Well, when you have coupled piles, you can randomly stack those two halves, and you have a 2-cycle with cycle length 6. So in some sense, we're like back to the beginning. Now, the cards will be scrambled quite a bit from what they were before, but that doesn't actually matter. It's still a 2-cycle. Well, being a 2-cycle to finish, think about it. If the top 6 cards form a certain pattern, you might even want to think of like 1, 2, 3, 4, 5, 6. There's some kind of pattern. And the next set of 6 cards also follow that same pattern of 1, 2, 3, 4, 5, 6. Then when we deal them out into 6 piles in this way, I've just run through all of the cards in one of the halves. And now this one will be the same as that one the same as that one, and so forth. Okay, so we'll just be building, once again, what's called a DMP, distinct mirrored pairs. But the point is, at this stage, these will actually match in color, guaranteed. Okay, so we will have perfectly matched them up in color, despite the many choices made by the spectator and the several mixing procedures that we put it through. Now, in the second sweep through this effect, I didn't do as much mixing, of course. I did in the original presentation. But the point is, we succeeded. We were able to take what seemed to be a random collection of 6 red and 6 black, and then mix, and somehow separate those so that they came out in this sort of way here, where each pair consists of the same color. Well, how likely is that to happen? Okay? How likely, so another way to think about it is, how likely is it that if you just mix the cards, I mean, genuinely just mix the cards, okay? And then you just started making pairs. Okay, I'll pair these together. Whoops. Pair those together, maybe these two together, and so forth. I mean, what are the chances that these all match in color? Well, pretty small, right? So we've got one there, got one there. Okay, blew it there. We're doing fairly well, probably because I didn't mix them very well. That's my fault. Okay, so there we go. We got 4 of them to match in color, but 2 of the pairs did not, okay? And so you can try that out. Just mix these 6 red and 6 black and then randomly put them in pairs, and it will take you quite a long time, by chance alone, to match them up in color. Okay, so it's pretty unusual for this to have turned out the way that it did. Well, we've been talking about ways of measuring the likelihood of certain outcomes, and in particular, the surprisal associated with certain random events, okay? So what is the surprisal associated with succeeding in the way that I did in both of those performances? Well, to figure that out, we have to first calculate the probability of doing what we did, finishing in the way that we did. What's the chance that that would happen just randomly? Okay, so that's what we're looking at today, is calculating the surprisal for any such performance where you have an equal number of red cards and black cards. And in the end, you match them up perfectly.